Instead of on Friday.
Did you hear that, Professor?
No.
Come on, just come on to the class, you know?
Wait, where am I talking into?
Right there, the box.
I wanted to ask if you would consider pushing the test back to Tuesday versus having it this Friday.
Yeah, great. I second the movement.
What are our thoughts on that? Since, we've already put that on the schedule and I've got people, probably planning around that. And, the struggle is if I change it, to accommodate one person, it probably messes someone else up, right? So
I don't think it's just for me. Wait, everybody put their hand up if they want the test to be pushed back.
Come on.
okay.
I think that's unanimous as far as I see it.
Okay. Yeah, I guess we can do that. I think that still gives us enough time to, get those, get them graded and back to you and that type of thing. Yeah, I was thinking it's like we do have a lot of things kind of all happening at once here between homework and labs and that type of thing. So yeah. Do you have a question or a comment?
Yeah. Can you hear me?
Yeah, barely.
They're gonna be. Is it to prepare for? Is it mainly gonna be homework 3 and homework 4?
I'm sorry. What was that last part?
They're gonna be like
homework 3 versus homework 4 on a test.
Yeah, is it gonna like how should we study for the test? Should we just look at those homeworks?
Yeah. So all right. So let's talk about this a little bit. So all right, I can make that decision. We'll change the homework, the exam from this Friday to next Tuesday. And so it will include convolutional block coding, convolutional coding, source coding, and cascaded noise figure analysis. And also, since we're pushing it back, we'll include some spread spectrum type of work also. All right, so yeah, so exam 3, I haven't written it yet, but this is basically what you should expect. I believe you're seeing this right now on the screen.
Yeah.
Yep.
Can you make it bigger?
So yeah, can I make it bigger? Yeah. So I haven't put a whole lot of thought into it yet. So but yeah, look at block code generation, block code decoding, understanding the concept of distance, and then and so this is essentially homework 3, right? And then this is essentially a homework 4, or actually, yeah, I did include a noise figure on homework 4. Obviously, some of this is rather tedious. So like a Viterbi decoder, it takes a lot of time to work through that. So we kind of have to keep things simple. But now I had intended to barely touch on spread spectrum in the exam. Since we're pushing it back, I think I can include a little bit more because you'll have time to study it and look at it. That's what we're going to talk about today. So so these things here, right? So let's look at homework 4 real quick. I assigned this last week. I understand that was over a holiday weekend, but trying to get you a homework assignment that you can go through and understand these concepts that we've been talking about. So the first one is using that same convolutional code that we went through in class, did an example on. So I'm just giving you a different input sequence. I'm actually giving you the output sequence. Okay. This is your answer right there, right? But you receive this sequence. And if you look carefully, okay, I think it's that one that's different, right? I think all the others are the same. So we've just got one bit that's an error. So you put this receive sequence into your Viterbi decoder. I think this is maybe a little bit longer sequence than we did in class. For the exam, I'll have to use a shorter sequence just because it's just a matter of time, right? And but this is the sequence that you should get out of the Viterbi decoder, and then you map that to the input sequence. So really, ultimately, this is your answer. So you're given the answers, but I need to see you run through this process using this code. It's the same constellation, same trellis that we did in class. You just are having a different received sequence, and therefore you will traverse through that trellis in a different way. Your metrics will be different and that type of thing that you calculate, but it's the same thing. Then this also very similar. I just changed a few of the probabilities, but it's the same step by step, right? And for the exam, I'll probably just give you a smaller alphabet or something to do. But then there's the Limple-Ziv algorithm, another source coding type of thing. Recall that for the Huffman algorithm, we need to know these probabilities a priori. That's how we build up that graph and how we sort things out, right? But with this, but that's not always easy to know, right? So the Limple-Ziv algorithm just does things on the fly, right? So again, step by step, exact same process we did in class, just a different sequence. For the exam, I'm probably going to have to give you a real short one. It might not even make a whole lot of sense, right? It'll be so short, but I just want to see you start the process and understand it. But it's going to be the same type of thing. And then this is the cascaded noise figure of the following circuit. Just remember that sometimes you work in dBs, sometimes you work in the linear units, right? I'm asking for the answer in dB. I'm giving you these things in dB. So work through that as it is. Excuse me. Another thing, a while back, people, particularly after the first exam, some people were pretty concerned about their grades. And so I gave you an opportunity to do some extra credit that's coming due. So yeah, you got a lot coming due this week. If you need more time on this, let me know. Okay, this is for you. This is a little bit of independently learn this. And so I don't think anyone's turned anything in on this yet. It is an opportunity though. So to add some eight points, total, right? So that's almost a grade level that you can increase. But I expect this to be, kind of a serious effort at learning an important topic in digital communications that we don't have time to cover, right? So all right, noticing a couple of people have joined us on Zoom. Not exactly sure when you guys joined. We did talk that we are moving the exam date from Friday this Friday until next Tuesday. So that will be, I guess, the 18th, right? So so no exam this Friday. We will have a lecture, obviously, and but we will have the exam on next Tuesday. I will send out a notice on the announcements, Moodle announcements thing, to make sure everyone understands that. So equalizers are an important part of receiver design. That helps you deal with the channel, reflections in a channel, and that type of thing. Low density parity check codes. There's also turbo codes are similar type of thing, and they are a very advanced combinations. They're a little bit convolutional in nature, but a little bit distinct and stuff. So but they're used in 5G and some other systems. So they're currently close to the state of the art, or they are the state of the art that's used in common commercial practice, right? So then carrier synchronization and symbol synchronization. That's how do you know when things are starting? How does your receiver know when to sample things and line up with all this timing that's happening at the transmitter? We'll touch on MIMO here in a couple of lectures, and but we'll just touch on it. There's a lot to look at in terms of propagation effects and this use of multiple antennas instead of just one transmit antenna, one receive antenna. If you look up at a cell phone tower, sometimes you'll see like 2 to 4 different antennas on there. If you look at your Wi-Fi access point, if it's one of those that has external antennas on it, you'll see anywhere from 2 to 4 antennas, right? And those are used to kind of overcome bad propagation effects. And then you can look at some very specific communication standards. This course is mostly concerned with the physical layer, the PHY layer of communication system. So you could look at these in detail. We'll actually talk about these today. Other topics, if you are interested in doing that extra credit, talk to me about that and stuff. So what this should do is that it should kind of be a type of thing where you're teaching someone about this technology, right? Maybe not a full-on lecture, but I want to see that you understand the topic deeply enough that you're able to educate someone else on it, and it's not just regurgitating what's in Wikipedia, Stack Overflow, or DSP related. By the way, Stack Overflow and DSP related are useful references to the practicing engineer, as is Wikipedia, but those are all I want you to go deeper than that. So all right, any questions on those? Again, if you need a little bit more time on that extra credit assignment, that's just talk to me, right? Shoot me an email and stuff. Also, if you have missed a homework assignment or I think the labs are due now, and checked earlier, I think there were a few people short. The expectation is that even if you did work like with someone else on the lab, I still want individual reports from everyone. And I believe as second semester seniors, you should have a good sense of what goes into a lab report. So I haven't been super explicit on that. I did give out some information though on that. So, but yeah, use use your experience and judgment to put together a lab report. If you are a little bit late on those, at the beginning, I said, but we really, as engineers, we need to do things on time. It's important to do that, but I still want to see you guys succeed in the course. So let me know if you're unable to make any submission, even back to homework 1, and I will make arrangements to review those and try to get you some credit for those. So let's not go into the final already in a hole. That's unnecessary, right? So all right, so let's jump into the lecture now, unless there's any other questions. Okay. Today we're going to talk about spread spectrum, touch on a little bit on low probability intercept and low probability of detection concepts. Look at 3 different examples of spread spectrum. There's maybe a few others, but these are dominant techniques. We'll look at frequency hopping a little bit more in depth, touch on code division multiple access, which is a form of direct sequence spread spectrum, and finally touch on Chirp spread spectrum. So what is spread spectrum? What do we mean by that? We purposely use a lot more bandwidth than Shannon says you need to, right? So if we remember back to Shannon's capacity theorem, it says that our capacity is equal to the bandwidth times the log base 2 of 1 plus the signal over the noise ratio, right? And so if we're attempting to achieve a certain amount of capacity, and we know that we have at the receiver, we've got a certain amount of signal power, but we also have a certain amount of noise power, then bandwidth ends up being constrained. At least, Shannon says that the capacity is more of a maximum that you could achieve, and it's up to you as an engineer to innovate and figure out how to approach that capacity limit. But it does drive the bandwidth, right? So if we need more capacity, generally we need more bandwidth. Now, if we've designed our system, bandwidth is typically a finite resource, and therefore we want to use it efficiently. So as many people can use that bandwidth as possible, right? But sometimes it makes sense to use more bandwidth than necessary, right? And spread spectrum is that example. So why would we want to do that? Well, a big reason is to overcome narrowband jamming or overcome jamming in general. So if you're in a adversarial relationship, let's say it's a defense application, which is kind of where spread spectrum was birthed. It was actually developed in concept in World War II. And it's always popular to mention that Hedy Lamarr, who was a movie star of the silver screen era back in the World War II era. She was actually quite a famous actress, but she was a pretty smart woman somehow at the same time, and developed this concept along with an engineering friend of hers. But there it was intended to overcome jamming, right? So if you're trying to communicate, your adversary, your enemy, is going to try to stop you from communicating. And so they're going to try to jam your signal. So this helps that. These concepts also apply in radar applications, and actually tend to maybe occur in radar before they get ported to communications, but it's a similar type of concept. So related to that, narrowband jamming is sometimes jamming isn't adversarial in nature. It's not intended. It's just kind of a consequence of spectrum sharing, right? So we have certain bands that are unlicensed. And one of the things that a license does is your regulatory agency says, okay, you're the primary user. This is how much bandwidth you get. This is where you can use it. This is how much power you can use. And you're going to be protected from other users, interference from other users. That's one of the things that a license really affords you. Now, but we also use these unlicensed bands, one at 2.45 gigahertz, another at 5 gigahertz, and one at 915 megahertz, and a few others, right? But the 2.45 gigahertz and the 5 gigahertz bands are really very popular because that's where our Wi-Fi operates at, and the Bluetooth, Zigbee, LoRa, all sorts of different services exist in these unlicensed bands. But you don't have protection from other users. So you've got to figure out how you can communicate while other people might be talking at the same time, right? So, we often use the example of being at a loud party, right? So you've got all sorts of different conversations going on between groups of people, friends, or whatever, and you're trying to be able to communicate with your friend, but you've got people having their own conversations all around you, right? So our brains and our ears are well adapted to this situation and do what I think is a remarkable job of it, of separating out these different conversations. Spread spectrum is one of the ways that we can do that in these unlicensed bands and allow simultaneous users to be communicating in the same spectrum, and do it without really cooperating, right? It's not like, okay, you talk now and I'll talk later. No, because these systems are disconnected. They're not, there's not even a control channel or whatever to be able to arbitrate, right? Your Bluetooth system is totally isolated from your Wi-Fi system. And someone else's Bluetooth that's sitting next to you is also disconnected from yours. So they're non-cooperative. It's not that they're arrogant and, fighting or anything like that. They're just, there's no means to cooperate, right? So, so other users appear as interference in your band. So spread spectrum happens with that. We also use it to overcome fading via frequency diversity. So let's look at, we've mentioned this topic, and it might have been something that I could put at the beginning of the semester. We're eventually going to talk about this. I think maybe on Friday, now that we swapped around the lecture and the test, but we'll spend a couple of sessions looking at some of these issues. But as you recall, I've mentioned a few times that sometimes in a communication path, you can have a signal that travels directly from transmitter to receiver in a straight line, and you might have one that bounces off a wall or a building or a mountain or whatever, and then reflects back to the receiver. And that is going to necessarily take longer to get there. It's a farther distance because we know from geometry the shortest distance between 2 points is a straight line. So anything else that's reflecting off of something is a longer path length. That means it's going to go through more phase more wavelengths, which results in more phase for these longer paths. Under certain conditions, the signals arriving at the receiver will be out of phase with each other. And therefore will create these deep notches. But because the distances can be measured in wavelengths, but wavelength is sensitive to the frequency that we're in, right? So the phase might cancel at a particular frequency, but as we deviate off of that frequency, maybe they add instead of canceling, right? So we tend to have these kind of notches in this propagation loss. So this would mean a lot of loss or very poor gain, right? So if you're trying to communicate here at this frequency, you're really going to have a poor signal to noise ratio, right? Because your signal is going to be attenuated or canceled quite a bit, right? And so if your signal to noise ratio, if your signal goes down, your signal to noise ratio goes down. And I think we've looked at enough of these to understand that our bit error rate is going to go up, right? So we're going to have lots of errors if we're trying to communicate at this frequency. Okay, now you could just decide, well, let's not communicate there, let's communicate there. But as we move, if we're driving around or walking around, then the path lengths change and the frequencies at which these things cancel is going to change also, right? So we, instead of using a narrow band communication that might suffer horribly from one of these notches, we're going to use a broader band, and we'll have some notches, but it'll we'll do okay because our energy, our signal energy, is now spread out throughout this frequency band. Okay, so all right, so some other concepts. So we can talk about covert communications. If you're most of us don't want others eavesdropping on our communications. In some situations, you don't even want to know, you don't want others to know that you're even communicating. And you probably don't want them to know where you're at when you're communicating. Our signals emit represent a signature, is what we call it. And that's kind of like saying, oh, here I am. You can attack me. In fact, we've seen in this latest conflict in the early days, some war fighters were not careful about how they were communicating, and they ended up being victims of some very effective targeting because of that, right? So we have a couple of a few concepts here we can talk about. One is, and these first two are almost used interchangeably, the low probability intercept and low probability detection. There's not universal definitions for these things. And but they both describe a basic concept, and that you want to make it hard for others to know that you're communicating to begin with, or the ability to intercept this signal. And you also don't want them to know details about your signal, right? What's your bandwidth, what's your communication rate, what's your modulation type, because the more information that is available to an adversary, the more they can jam you or mess with you or eavesdrop on you or that type of thing, right? So these concepts are originally developed in the field of radar, but also have applicability in communication. So you will see this often written as LPI/LPD, right? And so they're just grouping those together. So there's also an anti-jam concept, and this is a little bit more sophisticated. So this is an LPI, LPD might be worried that someone could find you. Anti-jam is an ability to communicate even in the presence of jamming. So spread spectrum helps with all of these things, right? It's not a cure-all. There's countermeasures to these two things, right? So, but that's another big motivation, right? So, the types of spread spectrum, these are the dominant types, and there's all sorts of variations and that type of thing. But we talk about frequency hopping, and we can do fast or slow hopping. Fast might be where we're jumping around to different frequencies over a large range of spectrum. And while we're trying to transmit a single symbol, we might be hopping all over the place, right? And at different frequencies. And contrast that to slow hopping, where we're hopping around in frequencies, but slow. And so we're sending a few symbols at one kind of average center frequency, and then we shift to another average center frequency, and we send some more symbols, right? And we do that over and over again. So and then we'll talk about direct sequence and chirp a little bit later. All right, so frequency hopping sequentially hops at different discrete frequencies within a large band using a sequence known to both the transmitter and the receiver. So the receiver has to know where the transmitter in frequency is about to transmit, so it can shift to that frequency and listen and decode the signal, right? So the receiver has to be able to follow the transmitter around. Often, not necessary, but it's convenient and easier to use frequency shift keying for our modulation, right? And so you can imagine that as we're hopping around, we're also deviating in frequency to modulate our signals, right? So that's a little bit easier to synchronize and implement in your receiver. So FSK is an easier implementation. We can achieve multi-user communications. Basically, we can have more than one pair of transmitter and receiver operating in the same band, as long as our hopping sequences don't land on top of each other at the same time, or at least very often, right? So orthogonal would mean that, let's say we've got two users in a particular band, and the sequences are created and synchronized such that they never land on the same frequency bin or slot at the same time, right? So they'll never interfere with each other. That's maybe the ideal. We tend to approach that, but there's only a finite number of orthogonal sequences, and it also requires this coordination. And so Bluetooth, for example, randomly assigns a sequence that is generated from its Bluetooth MAC address. It's burned into the chip at manufacturing time, and some connection parameters. Same like internet connection's unstable. Hopefully it's okay on that end. So sometimes in these semi-orthogonal cases, or particularly when you have lots of users trying to do this, you will occasionally land on the same slot, and therefore you will collide and you will have some interference from each other. You're probably going to have some bit errors, but we've learned that we can use convolutional coding, we can use block coding to try to do some forward error correction, or at least detect that there's an error, right? So we're seeing how all these different technologies are fitting together to help us effectively communicate. All right, some examples. Bluetooth is probably the most famous example, well-known example. You guys are all familiar with Bluetooth, I'm sure, at this point. Link 16 is a modern waveform used by NATO and similar allied forces in defense applications. And it's actually a combination of frequency hopping and direct sequence spread spectrum, but it's fundamentally a frequency hopping system. SINGARS is an older waveform used in defense systems, and it is a slow frequency hopping system. It's a little bit vulnerable to jamming, and so it's being replaced by JTRS, JTRS, Joint Tactical Radio System, I think is what it stands for. And that's more of a fast hopping type system. All right, so let's look at this. I've got a minute and a half left in this recording session, Zoom session. So let's start with an FSK modulator over here on the left. We'll go through a frequency up converter, RF channel, frequency down converter, and the FSK detector. That's all the same as a regular system, right? But you know, to up convert that to our place in a spectrum, we need a frequency synthesizer. Now let's program that using this pseudo noise generator, right? So pseudo noise means that it looks like noise, but it has some deterministic properties, right? Because we need to be able to replicate that on the receiver side. And in fact, it's got to be identical and synchronized to the transmitter's pseudo noise generator, so that what we do on the transmit side can be replicated on the receive side, and we can track it. Okay, so think about that as we jump to the other Zoom session here.